Hi everyone, I'm Shen Long, and this is my teammate and me. We're going to introduce our milestone tree. We chose the dark side of text to image as theme. Paper chosen is instruct pix to pix. Let's skip the setup section and start with seeing how instruct pix to pix works originally. Instruct pix to pix takes in an image and the text prompt and manipulate the image based on the text prompt here. Here is a dog image, and after manipulated the prompt, put a hat on the dog. Here is what the output looks like. We can see there's a dog wearing a hat. So actually, what do we aim for this project? We aim to implement an attack mechanism which will be applied to the output image of the intrapix pics. And the attacked output image will be harder to detect for detection system to classify. In other words, we want to fool the detection system with the attack without altering the image drastically imperceptible similarity. Now let's have a look at the structure of our attack mechanism. Here it is. Right. There are two main parts under this mixed attack mechanism. First one is the mixed attack, containing a deadful attack, containing a PGD attack, and also a simple random noise attack. After that, there's a blended backdoor attack. And let's look at the code. We uses ResNet 18 as the pre-trained model. And then we first define the deadful method. Then here is the define of PGD attack. And lastly, we pack them into the mix attack method. First, by applying the deadful attack, calling the deadful attack just now, and also secondly, call the PGD attack. And lastly, just adding a simple random noise attack. Beside those, here is the blended backdoor attack, which is a standalone one. So why do we apply so many attacks? By mixing these attacks, the adversarial image is more robust against defenses, where each attack has different properties. Deadful attack creates precise, minimal changes, but might be insufficient against more resilient models. PGD adds larger but controlled permutations, which increasing attack robustness. The simple random noise attack adds stochastic elements that make it harder for defenses to generalize the adversarial pattern. And lastly, for the blended backdoor attack, it plants a persistent trigger that forces the misclassification. And also, AI classifier could be trained with defenses specifically on some kind of adversarial attack, which makes them resistant to specific attacks. Thus, a mixed attack introduces varied permutations, increasing the chance of bypassing AI classifier models. Let's move on to the the defining of test methods. We uses a unified method for testing both clip-based and non-clip-based models against original and adversarial images. This part tests how well our attack mechanism can fool the systems. So for the clip model, it uses both image and text input during classification. For each set of images, which consists of the original and the adversarial image, we test the image against a set of text prompts. The softmax probability of the model's output are then calculated to assess the likelihood of each text prompt being the correct label for the image. And for the non-clip model, which means the traditional convolutional neural networks like ResNet, VGG, AlexNet, DenseNet, and MobileNet. These models uses only image inputs and are pre-trained on ImageNet. For each original adversarial image, the model produces a top 5 prediction, and the class IDs returned are mapped to their corresponding ImageNet class labels. Here are the code for the described functionality. The model test, which consists of a clip model or non-clip model. And this is the evaluation of it, right? And we also implemented the method which calculates the SSIM and the LPIPS, yes, which are the matrix used to tell how imperceptible the permutations are to human eye. SSIM helps determine whether the overall structure of the image remains intact. Basically, high SSIM value ensures that the structural details the human observes remain unaffected. In another hand, LPIPS evaluates the changes at a deeper features level, simulating how human perceives differences in texture, colors, and small details. And the lower LPIPS indicates the attack has been able to fool the AI system while remaining undetectable to human observers. The last implementation at the testing section is about showing how different the adversarial image is from the original image. This method checks and visualizes the difference between the original and the adversarial image. And here's the code, it's quite short. And now I will pass the presentation to my teammate Emin to proceed with the rest of it. Thank you.
Thank you, Xianlong. Now I will move on to describe section 4, which is on testing the pix-to-pix prompts outputs against the adversarial noise outputs. So you can see below, there are a total of 3 sets of images we use for testing. First is dog, then next is sculpture, and lastly is human. So now let's proceed to the first set, which we prompted to pix-to-pix, which is turn the dog to red color. As you can see here, the prompt is stated turn the dog to red color, and we've initialized our constants as seen here. Then moving on, we've attacked the pix-to-pix image using mix attack first. Then afterwards, we use blended backdoor attack to increase the effectiveness of fooling the test detection systems. Then after the test images were attacked, we can see the output below. This was the original image from the instruct pix-to-pix. Then after that is the mixed attack with PGD. Then this is the mixed attack with PGD. And here it is with the blended backdoor attack. So now we move on to the test detection. So firstly, we start with the clip detection, the clip testing, and then we'll move on to the other CNN tests. So as for the initial clip testing, it combines the images and text learning, making it resilient to minimal perturbations. As you can see from the small drop from 0.75 to 0.6. This reflects this robustness, but similar categories like pink and orange did cause some confusion due to the subtle noise that we added, as you can see here. It increased from 0.09 to 0.11 for orange, then pink is 0.14 to 0.23. Now, as for the other CNN testing, ResNet 50 is reliant on deep residual learning, makes it sensitive to gradient-based attacks like PGD, misclassifying as teddy bear, as you can see here. It shows its struggle with perturbations that target specific textures learned from its image net training. However, Overall, it still shows Golden Retriever as its main option. As for the other tests like VGG16 and AlexNet, these models with simpler architectures and reliance on pixel level features are easily fooled, as the first options for the adversarial aren't Golden Retriever but instead other options. As you can see here, it is Standard Poodle, and for the bottom one is Teddy Bear, instead of it being Golden Retriever. Now, this shows that the sequential design of VGG16 and the fewer layers in AlexNet makes them more vulnerable to adversarial noise, shifting prediction significantly. As for the last two tests, which is DenseNet 1-to-1, it has dense connection across layers to improve its feature propagation, making it more robust. So it retained its high confidence in Golden Retriever due to the holistic feature capture, even though it did show some minor misclassification. As for the last one, which is MobileNet v2, its lightweight design is less resistant to adversarial attacks, leading to high confidence in Kuvaz instead of Golden Retriever. It is less robust than DenseNet due to its focus on efficiency. As for our next test method of structural changes, SSIM and perceptual differences, LPIPS. If the SSIM value is below 0.5, then the images are noticeably different to human eye, while if LPIPS values are closer to 1, it will indicate significant perceptual differences. According to the results below, as you can see here, SSIM shows as 0.7, which is a moderate SSIM score, which indicates that while some structural similarities between the original adversarial images remain, there are still some notable differences. As for LPIPS, it is only 0.17, which is very low, showing that the perceptual similarity is high, meaning that the adversarial changes are subtle and not easily detectable to the human eye in terms of the texture and spatial details. As for our last test method, which compares the difference of adversarial perturbations on images with the darker and lighter areas, it represents regions where the intensity of pixel change was more significant, with the lighter regions showing where the adversarial perturbations had the most noticeable effect. But anyways, despite these changes, the overall structure of the dog still remains intact, as you can see here, suggesting that while the noise did affect the image, the modifications were subtle in terms of the perceptual similarity, as we can still see the dog. And now, since due to time constraints, I can't describe the result of every prompt. However, I'll give some notable highlights of any interesting prompts. First being turn the sculpture to wooden. So for turn the sculpture to wooden, the steps taken here from manipulating the image using instruct pix to attacking the image and testing, it's still the same as before. But this time, from the test results on the clip, it can be seen that the probability for wooden dropped massively from 0.99 to 0.27, while metallic increased from 0.1 to 0.55. This indicates that the adversarial noise confused the model's material recognition, and Clip's multimodal training made it somewhat resistant, but still led to a misclassification between similar textures like wooden and metallic. As for the other test models, the class labels were quite strange, but despite that, we can see that the adversarial attacks has indeed proven to be effective. As for ResNet, it has a strong classification of 0.87 for swimsuit, despite the original picture being a sculpture. This can also be seen for DenseNet 2, which also classifies swimsuit as its highest. MobileNet also did misclassify too, with a 0.4 classification for Visalia, which is actually a dog breed, showing a strong susceptibility to noise due to its lightweight architecture. As for the SSIM and LPIPS, just like dog, it still shows a relatively low score for SSIM at 0.4, showing that the attacks has still kept the overall shape and the form of the sculpture. As for the LPIS, still has a low score of 0.32, which suggests that the perceptual difference are still not that different, but it is still higher than smiling and crying prompts. As for the difference between the original and adversarial image, the overall structure and silhouette of the sculpture still remains intact, but it is less discernible compared to the other sculpture prompts. As you can see here, this is the wooden one, and even if you look at the crying sculpture, you can see that it is more noticeable. You can see the sculpture pattern better. Now we'll move on to the last, which is the human set, and this is to the prompt of make him cry. It appears that for clip testing, if you move below, that the model's probability for sad dropped significantly from 0.19 to 0.002, and increased for from casual of 0.45 to 0.73. While this shows that the clip's emotional classification was disrupted, with adversarial noise causing confusion between the emotional and casual expressions, showing that while clip is robust, it still struggles with emotional cues and are subtly altered. As for the other testing, since it can't understand text prompt, it just stated the most visually identifiable item, which in this case is the suit. Since the image is mostly, you can see it's a suit. So adversarial noise outputs, it still did not change the outcome much, as you can see below here. Then as for the SSIM and the LPI-SIS, just like the previous prompts, they all have a similar result. And the difference between the original and adversarial visualization shows that the modifications were subtle in terms of perceptual similarity, so it can still be interpreted by human, as you can see. Then the next section is just a bonus mark category for the previous milestone. So I'll just move on to the next section, which is the final section on overall analysis on results. So as you can see from the bar plot, it can be seen that the highest impact of adversarial noise on the clip test is the prompt turn sculpture to wooden, with the probability drop from original to adversarial of 0.7, with the next closest being the emotional prompts like cry or smile. The least impactful of the adversarial noise is prompts which is something to do with breed, like turn dog to husky, or turn dog to a cat, or something easily identifiable for the testing system like a t-shirt. Now, in general, adversarial attacks were most effective on sculpture images, as models rely heavily on texture and geometric patterns for classifications. Small perturbations also disrupted these patterns easily, leading to frequent misclassification, especially in non-clip models. And dog images also performed well in fooling models like ResNet50 and VGG16, which focus on the textures, but clip remained more resilient due to its multimodal training. Human images were more resistant to attacks, as models are extensively trained on human-centric datasets, making them simply better at handling subtle adversarial noise. As for the perceptual matrix, SSIM and LPIPS showed that actually sculpture images had more perceptual changes, while dog and humans maintained a better perceptual similarity. But overall, human-related models were the most robust, while sculptures were more vulnerable due to their rigid and easily disturbed structures. Lastly, it can be seen from the plot, which shows that the adversarial perturbations that are from all prompts for the overall structure and silhouette still remains intact, which suggests that while the noise did affect the image, the modifications were subtle enough in terms of the perceptual similarity, which means that it can still be perceived by a human. And here is our references that we use for this. Thank you.